Hello everyone, I'm Xinkong from Zhejiang University, Hangzhou, China. I will introduce our work, Semantic Graph-Based Place Recognition for 3D Point Clouds. Loop closure detection is an important issue in SLIME, which refers to the ability of robots to recognize whether a place has been reached before. It's the most effective way to eliminate the cumulative odometry drift error, helping build a more precise global map and achieve more accurate localization. This is an illustration of place recognition. It is a reverse loop closure in sequence 8 of Kitty dataset. Note that the heading direction of the two frames are almost exactly the opposite, which brings a challenge to existing method. The goal is input 2 point cloud scenes, calculate their similarity score to indicate whether they are in the same place or not. There are a few challenges to this task. Firstly, the place recognition based on image is well developed, but there is no good solution based on point clouds. Large-scale point cloud is unordered, sparse, and distributed widely. It is hard to obtain stable and effective features, and point clouds are lack of texture information. Semantic information is stable, but how to effectively use semantic information, and how to reasonably measure the similarity between point cloud scenes. In practical application, the algorithm should be robust to dynamic occlusion, viewpoint changes, and low time consumption. Most of the existing methods focus on extracting local, global, and statistical features of raw point clouds. We compare the recent state-of-the-art open-source works, M2DP, scan context, and PointNet VLED, which are marked in bold in the text. I will quickly go through recent sorter methods. M2DP projects a 3D point cloud onto multiple 2D planes and generates density signatures. The left and right singular vector of these signatures are then used as descriptors for the 3D scene. However, it relies on the distribution of all points, and the performance is not satisfied when there is a partial loss of points. LocalNet projects a 3D point cloud onto bird's eye view and uses a contrastive convolutional neural network to get the final feature vector. Scan context reserves the maximum height and maps 3D point clouds to 2D planes by histogram statistics. To achieve rotation invariance, it calculates all possible column-shifted scan context line by line to find the minimum distance, requiring longer search time but usually performing better than other methods. SegMatch and SegMap present a high-level perception, which segments point clouds into a set of discriminative elements at object level. They use a 3D CNN to encode segment features and identify candidates' correspondence by using KNN in feature space. This approach is a successful attempt towards humanoid perception. Nonetheless, it needs a dense local map, and the relations among objects are not taken into consideration. PointNet VLED combines PointNet and NetVLED, which is the first point cloud network to directly handle the point cloud scenes in 3D space. But the local feature extraction and the spatial distribution of local features are not fully considered. Sequence LPD and LPDNet extract features in both feature space and Cartesian space, fills the neighborhood features of each point, and use NetVLED to generate the global descriptors. The above methods process a large number of raw points and achieve unsatisfactory performance when the point cloud scenes rotate. Here is our motivation and contribution. Humans perceive the environment by distinguishing scenes through semantic objects and their topological relations. Inspired by this, we present a new approach that converts the raw point cloud data to a novel graph representation by aggregating the semantic information. Such graph representation retains critical information and considers the topological relations, making the expression of the point cloud data more efficient and comprehensible. Moreover, we apply a learning-based graph similarity computation strategy to solve the retrieval task instead of simply calculating the Euclidean distance of feature vectors. Experiments on the Kitty dataset show that our approach achieves state-of-the-art performance, especially for reverse loop closure detection and robustness to occlusion as well as viewpoint changes. This is our framework. It consists semantic graph representation and graph similarity network. In the graph representation part, we firstly adopt off-the-shelf methods like RangeNet++ to get the semantic segmentation results, and then get instances by clustering each semantic objects. Finally, we convert semantic instances to semantic graph. Place recognition is now modeled as a graph similarity measurement problem. So we propose the graph similarity network, which consists node embedding, graph embedding, and graph-graph interaction. And finally, after a few fully connected layers, we can get the similarity score of the input two-point classes. As we can see, semantic objects are represented by nodes or superpoints. Their semantic labels and coordinates are reserved in the node feature. Their relations or interactions are transformed to edges, constructed by KNN in both feature and the Euclidean space. We can regard the point cloud scenes as graphs, and the place recognition is modeled as graph similarity measurement. In node embedding, we adopt edge count from DGCN to capture local geometric information, while guaranteeing permutation invariance. The graph edges are dynamically updated by KNN in feature space, instead of fixed. As independent convolution is more efficient for multimodal features, we perform feature aggregation separately on spatial and semantic level, and concatenate the output features together as the final embedding of each node. In graph embedding, we estimate a learnable weight matrix associated with each node by an attention module. We let the neural network learn which node should receive higher attention and be more representative of the overall graph. Finally, we acquire the graph embedding by the weighted sum of node embeddings. In graph-graph interaction, the relation of a pair of graph-level embeddings can be accurately estimated by a neural tensor network, NTN. The model computes a feature vector to measure the relation between graph-level embeddings. In experiment, we evaluated the proposed method over Kitty-odometry dataset. The ground truth poses are used to determine if there is a loop closure. The ground truth is either 0 or 1, as we simplify this problem to a binary classification task. We train the model with a binary cross entropy loss function. We use both RangeNet++ predictions named IROS Rn and the semantic kit label of the SK as front end, comparing with M2DP scan context named SC and PointNet VLED. Specifically, for PointNet VLED, we use both its pre-trained model PVPre and the retrained model on Kitty PVKitty for a fair comparison. Our performance is competitive, especially for the challenging sequence 8 with reverse loops. Most of the existing methods cannot handle the viewpoint variations, where our approach performs consistently. Notably, the LU of RangeNet++ is only 52%, which is not high and will introduce noises, like wrong labels and centroid offset. Though ours Rn is indeed lower than ours SK, it performs satisfactorily, which indicates that better semantic prediction will bring improvements. Here we show some quantitative results. We randomly choose a specific single scene and measure similarities between it with other scenes in each sequence. Then we color the trajectories according to similarity scores, as shown in left upper. In fact, only the scenes near this chosen scene within a distance threshold should be similar. We find our predictions are distinct and accurate. Visualizations of node attentions in graph embedding is shown in right lower. We observe that nodes closer to the center receive higher attention, while fake nodes receive lower attention. We also test robustness from occlusion, viewpoint changes, and distance thresholds. In a real scenario, dynamic objects like person, vehicle inevitably occur during long-term localization, which brings occlusion in later point clouds. For validation, we randomly select a certain angle in the azimuth and remove points within this area. In practice, the viewpoint often changes when arriving at the same place. Thus, it's crucial to handle the viewpoint changes. We randomly rotate the point cloud's heading, and the results are shown in table. Our method shows great robustness to occlusion and rotation. For specific task and application scenario, Different distance thresholds or positive pairs for loop closure is needed. To evaluate the adaptability of our approach, we adopt thresholds of 3, 5, and 10 meters to train the corresponding models. Our approach can maintain satisfactory performance. Our graph similarity network is lightweight, fast, and capable of obtaining similarity scores for n places via a single pass through the network, instead of comparing them one by one. With a batch size of 128, the inference only takes about 9 milliseconds on the GPU, making it applicable in real-time robotics systems. It's a demo video in 1 minute. It's raw input point cloud and semantic segmentation results, and we get instance segmentation results. We convert them to semantic graph representation. Through our similarity network, we can achieve place recognition. It's our network structure. Node embedding, graph embedding, and graph-graph interaction. We get scores. And this is the experiment results. And the robustness test. Thanks for your attention. Our code will be available on GitHub, and discussions are welcomed.